In collaboration with Kanne School, and by utilizing participatory design methodology, we created an interactive AI mobile application meant for teaching 7th grade students about astronomy. In insight into teaching practices and materials at the school, we conducted a field study. This became our first meeting with the key stakeholder, the science teacher of the 7th grade class we will be collaborating with. The visit included a 1-hour semi-structured interview, which we recorded for analysis. Here the teacher shared how lessons are structured and what materials are used. We were surprised to learn that students rarely use physical materials, not even a main textbook. Instead, they relied heavily on digital learning tools. The only physical items in use were a solar system model and some inflatable planet models for demonstration. Our main takeaways from the field study were to focus on integrating the real world, facilitate new novel experiences, focus on interactivity, and making it easy to use. Based on these design pillars, informed by the field study and the themes provided by the teacher, we designed and implemented 4 prototype exercises. An exercise where you can drive a Mars rover around, an exercise for experiencing gravity on different planets by throwing virtual tennis balls, another exercise where you could play ping pong with water in zero gravity, and lastly an exercise where you could see through the layers of the sun, comparing the size of different planets to real-world objects. The second visit to the school, he facilitated a workshop designed for direct collaboration between us, the students, and the teacher. We wanted the students to reflect on their current learning practices while imagining new possibilities. Their input would then help guide our design process. We based our workshop on methods from participatory design, specifically our own variation of the future workshop approach by Jung and Müller, combined with the inspiration card workshop by Halsgaard and Dalsgaard. We call it the inspiration board. During the workshop, students worked in small groups and were given 19 subject cards. Some were subjects in the current curriculum, others were new but related topics. They sorted these based on what they thought was interesting to not interesting, and what was easy to difficult to understand. This helped us map out what topics were exciting to them and what subjects were hard for them to understand. Students then got hands-on time with our early AR prototypes. This made them reflect on their own ideas while also grounding their expectations in what realistically achievable with today's technology. After the workshop, we went back to work to polish and create a final application based on the feedback from the workshop. For example, it was clear that many of the students thought that the Big Bang and the expanding universe was both interesting but also hard to understand, while the Mars rover prototype was fun to interact with, which prompted us to incorporate these themes as an exercise in the final version of the application. The final application ended up consisting of 3 exercises: Big Bang, Mars rover, and Earth's composition. The Big Bang exercise gave the user the ability to see the Big Bang in real time, and then control the timeline by moving back and forth in the room, simulating how light years represent both distance and time space. Mars rover exercise gives the user the ability to control a rover and to look for signs of life on Mars by collecting rock samples around the room. Lastly, the Earth composition exercise shows the user our planet and its many layers, making them dig through each and learning about their content. Our third visit to the school focused on evaluating the AI application we had developed. The goal was to see how students interacted with it, how effective it was at teaching about astronomy, and if we fulfilled the ideas from the previous workshop. Before using the app, they completed a digital quiz to test what they already knew as a baseline. Then we brought the AI application to the classroom and let the students explore it directly. As the students used the app, we logged their input and provided assistance in case they had questions. After they had tried the application, we asked the students to fill in a digital form about the subjective experience with the application. In our evaluation at the school, our results show a moderate non-significant increase of 19% accuracy between the pre-quiz and the in-app quiz, indicating a positive effect on short-term knowledge gain among the students. These results should be considered indicative and not conclusive, since the quizzes weren't set up to strict scientific standards. Meanwhile, the qualitative feedback from the students indicated 65% of the students reported wanting to use similar apps more, while 41% were more interested in astronomy afterwards. Many students also mentioned how fun and educational the app was, highlighting those two aspects in our thematic analysis. The teacher told us that in general, the application would be a nice addition to our teaching, supporting the understanding of abstract astronomy concepts through visualization and interaction. In conclusion, through a comprehensive participatory design approach, we created an interactive AR mobile application, which was co-designed in collaboration with both students and teachers. As part of the process, we also created our own workshop exercise, which enabled students to easily discuss and relay what topics they found difficult or interesting. Through our evaluation, both the students and the teacher expressed interest in using the application again in the future. While many students reported finding the app fun and educational to use, this study therefore shows the promise of using interactive AR for educational purposes, creating more engaging and fulfilling science education.